Okay, so good morning, everybody. So as Mark said, I'm Moty Fania, Senior Principal Engineer in the Advanced Analytics team, and with me we have Assaf Araki, which is a Senior Architect in the team. And I'm going to talk about how we in Intel solve a high-value problem with big data analytics and share some of our insights in that domain. So a bit about the team, just as a background. So basically, we are a team located in Israel, and we have a cross-corporate ownership for advanced analytics solutions. The team charter is to solve internal problems that could yield high value by applying advanced analytics and big data, but also to leverage the same capabilities to grow Intel revenues. So the key technologies or the key specification that we have is big data and machine learning, and the skills are mostly software engineering, decision science, and business acumen. So this is about the team, and I would like to begin with this probably most of you probably saw this maturity curve from Gartner. And this is a maturity curve that demonstrates how you could get value out of analytics. So data is sometimes overestimating. I mean, we talk about data and we put a lot of emphasis on it, but data until you do something with it is almost meaningless. So this shows how you could achieve value, and it goes from the low end, which is the traditional report, traditional BI, up to the higher end, where you are able to use the same historical data to predict future things. And this is where it becomes much more valuable and interesting. And more than that, if you can take action based on this prediction. So we were doing this kind of work at Intel across the spectrum for a long time. The one thing that we understood is that we were doing it based on the data that we had in our traditional system, the enterprise data warehouse, the databases from many kinds, but we were not using other kinds of data. Data that didn't fit into the columns and rows and the tables that everybody has in its data warehouse. And when you ask yourself why, you get to the same, basically the characteristics that define big data. Either the data is in too high volume, either the data is very unstructured and doesn't fit into the traditional system where you are used to work with, or because of the pace of which the data is being generated or has to be processed, the velocity. And when we had understood this, this is the point where we have decided to make a change and to prioritize big data within the enterprise. And this was approximately 2 or 3 years ago where we decided it. The first thing to do was to, as I said, to understand that this is a priority. This is the stage where we have built a competency center at that domain at Intel for big data analytics. And basically, the first step was to build the infrastructure and to build the skills within the competency center. And this is something that is important because the skills are not, big data skills are not the same skills that you'd expect from a traditional BI or traditional report developer or BI developer in an organization. So building this skill and building the infrastructure, and again, many people tend to forget or to think that big data is only Hadoop or one kind of thing, and there isn't one size that fits all. So we have basically defined what is the right mixture of technologies, of platforms that can give us the right way to solve problems. And then once we have this kind of infrastructure and we have the skills, this is a good point to start and generate value out of it. And as I said, to go and identify the problems, the pain points that different organizations at Intel has, and try to apply what we know and what we do to solve the problems. And this was the stage where we coined the term 5, 6, 10. This is just a term that we use that says 5 people for 6 months are expected to resolve a problem that is $10 million or more. 5, 6, 10. And this is just to highlight how we prioritize our projects. I mean, to begin small teams for short period of up to 6 months, generating high value. And this is how we started. We had one project like this in 2011. In 2012, we have 12 like this. And actually, today, we are targeting, as I will show you in the next slides, problems that are in the magnitude of $100 million and more. So this is basically an evolving, and it's successful. We began the process with approximately 19 employees. We are now talking about 100 employees who are doing that. So with the results, there is a momentum of success, and the team grows. So let me just give you a glimpse of what we do in terms of solutions or use cases. So so first, as you know, what Intel does is to manufacture chips. Most of the things that Intel does: design them, manufacture them, and then sell them. So these were the first, or the places where we began, where we said, if we could do things in these domains, it could yield a very high value. The first thing that we found is that we had a lot of data that was collected in manufacturing domain. I mean, in the process of manufacturing, for each chips, thousands of metrics are being collected as part of its early stages and the manufacturing process. And this data was rarely used. It was used mostly when something goes wrong for forensics or something like that. But what we found that if you could take this big data and use it to personalize the treatment that you give to each unit, to each chip, you can get much better results and make much better decisions in the later stages of manufacturing. And just to give you an idea, saving 1 second of test time for a unit is the magnitude of $5 to $10 million in high volume manufacturing. It's very significant. So by being able to give this personalization, we are able now to make much smarter decisions in different process of manufacturing, how you package it, how you determine the voltage, how do you determine other aspects of each chip. And this is definitely something that can go and get to the range of the $100 million. We are targeting it the range of $100 million in 3 years. In the chip validation, it's the same thing. Each chip becomes extremely complex, billions of transistors, and the question is, how do you know how to test it effectively, efficiently, with all of the combinations? And we have used the data that was there to be able to make much better decisions of how to reach coverage faster, how to know when to stop, how to handle bugs effectively, efficiently, when in the past you could assign, because you saw different symptoms, you could think that you need to assign different teams to solve the same bug. But by using the data, we are now able to better identify the root cause of the bug and bugs and handle them better. Other examples, it's distorted a bit, but security. So we have used big data analytics to do better job in identifying advanced threats in our organization. We have huge amounts of data in different logs of security, and we would like to be able to use it. So this data was scattered all around, 100 terabytes of data being generated each year, and what do you do with it? So by integrating this data and trying to correlate different aspects, proxy data, logs data, DHCP, VPN, just to give you domain controllers and so on. So by correlating this data, you are able to detect anomalies and activities that could not have been found otherwise. And I'm talking about advanced threats with command and control characteristics. Sales and marketing is another example, where instead of just using the internal data that we had and always used, we were able to use data from the outside, data about competition, about the market, about web usage and so on, and by that to help our sales force to be able to much more effectively find which accounts to address. You had hundreds of thousands of accounts. How do you know which one to begin with as a salesperson? There's always a limit capacity of how many accounts you can handle. So answering questions like who to address, what to offer, and when to trigger, and other kind of these questions is very significant. Other kinds of solutions that are somehow more external in nature, we have few examples of them. One of them is the context-aware, location-based recommendation system that was based on Mahout on top of Hadoop and allows us to basically provide targeted offerings to navigators who use a navigation app in order to maximize the conversion rate. So it's basically takes in considerations both location, context, and other aspects in order to do that. Other examples that I could mention here, I didn't put them on the slide, but in the domain of Internet of Things, we are building an infrastructure that allows us to ingest data from millions of devices and to be able to apply analytics on time series in order to do that. And we can also use this in the health context. And we are part of research in the Parkinson's disease that allows us to basically put wearables on Parkinson patients and to collect the data and to apply some analytics on top of it. So a large range of use cases where we got a very nice value out of it just from sales and marketing. Last year, $69 million of growth in revenues, very significant, and so on and so on. So this may sound as if it's ideal and everything is good, but this is with the point where I would like to transition to Assaf. He can share with you some of the challenges that are associated with it. Thank you.
So I'll talk a little bit about the challenges that we had and we are still having in the environment. So we are dealing with big data or distributed computing environments, clusters, and the first challenge is coming from the platform itself. There are a lot of platforms of big data. I think over 200, 300 solutions in the market. Some of them are open source, some of them are none. And not all platforms support code, especially the structured one, and even if they support the write-on code, each one has its own flavor of code. Most of the platforms are specialized. They're either analytical or operational. Their storage structure is different. Some are in key values, some in matrix, some in document. And they support different data loads. Some are more like batch oriented, other are only streaming data, and last is the solutions are immature. We are only on the dawn of the big data. If you look on the peak of Gartner hype curve, we are reaching the high curve itself, the high point in the curve. So we understand there is no solution, as Moty mentioned, one solution that we can use. We need to build a platform that combines several clusters to answer the needs. The other challenge is from the algorithm perspective. We are talking about algorithms which have several characteristics. It's on a distributed platform. It needs to have a state dependency. We don't want to move the data too much, and it's very iterative and consume high CPU and I/O. And for that we see what we call the distribution curse, which means that because of the distribution, most of the algorithms right now today in the market are written sequential. There are some distributed algorithms. A lot of the platform have the same algorithms. We just talked about it this morning, that implemented all over again, but adding the breadth of the algorithm that have in the market to the distributed community is not an easy task. It needs to be redesigned and rewritten. And even it's been written for one platform, it's not suitable for the processing method of all the distributed platform, because each distributed platform has its own processing method. And there is no really cross-platform code. You need to write it for each platform. So we came with solutions that it's hybrid and it's combined two basic capabilities. We're talking about the offline, which is the batch, and the online. In the meanwhile, while as Moty mentioned, we as well added another platform of stream, but let's concentrate in those two. So each one is not one solution. It doesn't mean that, you know, for the batch you only use Hadoop, for example. You can have probably more than one solution, but we don't want too much. And the offline, it usually takes the raw data and the algorithms and calculate the model itself, find the patterns, but it's not suitable for interactive queries. And for that we have an online platform that combines the model itself and the latest data, because a model in the batch offline may be learned once a week or once a day, but still in context recommendation, we want to give recommendation and know what the user got 5 minutes ago. So we need the historical data of the last day, combine it, and give a prediction. And we use those platforms for all our solution in production. Most of our solution over 42 days. If we look for the trends that already started and here in the market and starting using it, we can identify three trends in the big data domain. One trend is called Hadoop 2, or called Yarn, yet another resource negotiator. In Hadoop 1, for example, we have the file system, HDFS, which is the file system management, and on top of it, the MapReduce, which is the processing method. The problem is that the processing method was combined with the resource management. Hadoop 2 is separating that. Yarn is only resource management, and you can run any processing method on top of it, which means you can run MapReduce as there is here, but you can run as well maybe columnar database. You can run our stream analytics. You want to do graph analytics like Giraffe or GraphLab. Or you want to use MPI or any other, you can use on cluster. You have the same resource manager that manage it. This is the first one. And that means your data is residing in the same place. You need another processing method. You do it in the same place. You hopefully in the future no longer need to move your data too much. The other trend is rising is in memory. These jobs are very iterative, a lot of writing and reading from disk between iteration. We want to avoid it and run our training much faster. So one leading is the Berkeley data analytics stack. I'm from Berkeley and especially Spark within it, which is instead of distributed disk, it's a distributed RAM mechanism. It supports batch, interactive, and stream in one place, and it's basically on top of Hadoop itself. So you see here a solution of storing the data and managing the data Spark in the RAM. On top of it, you have a solution for stream, for SQL, for graph analytics, and for machine learning library. So and this in memory give us the capability to run our processes faster, learn faster, and the performance for each iteration. If we compare it to Hadoop, the first iteration is basically almost the same, because we need to read the data from the disk and calculate. But if you need to do 10, 20, 30 iterations, then the gap becomes much and much more bigger. So in order to advance the research in this area, we jointly with the information system engineering department here built a cluster that over 200 terabytes. We installed on it Hadoop 2 and Spark. We support it, and we focus now in development of new machine learning distributed algorithms on those platforms, both for researchers that can do the research here, so companies that have research questions, and from curriculum we run a mining data sets course. We did it first last year for master students, and we are continue to deliver it. So just to summary, we leverage at Intel big data analytics to achieve to solve high value business problem and get benefits either by reducing cost or increase productivity or revenue. Big data offer a lot of challenge, not only systems but skills, a different set of skills from the data scientists and from the developers especially. And we are not having a team of researchers and a team of developers. They are all doing it together, working together. There is a knowledge of development for the data scientists and needed knowledge in machine learning for the developers as well. The trends that we identify is Hadoop 2 and in-memory, and we're going that direction. And lastly, the lab at Ben-Gurion University is support research, and if you have interesting questions, we'll be happy to help. Thank you.
Okay, thank you very much.
אם לא טעיתי ולא החמצתי, לא שמעתי את המילה סטטיסטיקה או כלים סטטיסטיים, ניסוחים סטטיסטיים, בידי אף אחד מהדוברים, שניכם. השאלה היא האם זה לא רלוונטי קצת גם למה שאתם עושים.
In English or in Hebrew? Okay, so I'll answer in English just in case for the others. So in the term, when we say data science, it incorporates in it machine learning, data mining, statistics, all of the above. So basically, any way of being able to use historical data and be able to predict based on it is relevant. So it's not only statistic, it's not only machine learning, it's a combination. And the term that we use is broader when we say data science. Hopefully it helps.
Can you give me an example of a data item of an event that would go into the database and how it is being entered, registered, and perhaps coded?
So it depends. I mean, so there are many ways, many routes where the data could flow in. So in the traditional way, your ERP systems would be the one that will generate the data, and it will flow usually using ETNL tools into your enterprise data warehouse. This was the traditional flow of data. Today you have other kinds of flows, especially with the context of big data. You have a lot of external data that is originated from logs, from the web, from social media, data that is originated from machines. As I said, Internet of Things, it's wearables, it's devices out there. Any device could send information. How it flows? So it flows network. I mean, it gets through the network. In different protocols. For the Internet of Things, it uses the MQTT, flows into a broker, and then from the broker it gets to the big data container through different levels of ingestion. So it really depends on the context, on the application, yes.
Can I just, when I look, a typical ERP system will include hundreds of thousands of data events like that. Each one of them, or not all of them are consistent. If I look at my database, even the trivial thing like defining a customer name may take many permutations, customer state. Even a country picture was. When I entered the country like Costa Rica in my ERP system, before there was the prepared list, some wrote Costa Rica with a hyphen, some without a hyphen. And so also the level of ambiguity within ERP systems is quite large. How do you cope with that?
You're right. There are different stages of cleansing the data as part of ETNLing it into the system. So it's the process of being able to bring the data first and then apply different aspects of either cleansing the data, preparing it, enriching it. And this is a process, and it's always a challenge. I mean, what you're saying is always a challenge, and you have to invest. And some of the solution is to invest in preventing the problems to begin with in your ERP systems. And some of it is reactive. Once you get the mess, you try to deal with it. But there's no one solution that I can give you that solves everything. It should be in both sides, both the source system and once you get it into your system. Yeah.
Maybe to formulate it in a different way, are you dealing with unstructured data?
Yes, of course. So big data, in many cases, is unstructured or semi-structured, and we deal a lot with it in what we do. This is the big change that I mentioned at the beginning, where instead of just using the data that was in the databases and was structured, we are now finding a lot of value by using data that is unstructured, that has the characteristics of big data, the 3 Vs or 4 Vs or whatever, how many Vs you want to put there.
So thank you very much again.